So today we will start a new topic uh, that is on decision tree. Uh, it is from chapter 3 of this book that, by Michel's book on machine learning. Now we have already discussed how concepts are represented. In the previous topic itself, we have seen that a concept can be represented as a Boolean expression. We will still continue with that kind of representation. And in particular, we have put certain restrictions on the representation of a concept, like conjunction of attribute literals of an attributes. Okay, so or attribute literals, if we say. So we can consider that is the only form of representation of a concept. But when we represent a Boolean expression, for example, this is one kind of concept, one kind of Boolean expression, which means that with certain attribute whose value is sunny, and then another attribute, for example, attribute could be sky, and then the temperature could be hot, and then humidity would be humid, and the wind condition may be windy. So these are the literals. If it satisfies this condition, then only the output would be 1, or output would be true. Otherwise, it would be false. So in this way, we have represented concept, and we have considered certain forms of literals which will take either a single value of attribute or all values of attribute or none of the values of attribute. So these are the only possible form of literals in the expressions. And we know that this cannot represent all sorts of target functions in Boolean expressions. So if we consider another kind of representation, now decision trees will give you that power of representation where any kind of Boolean expressions with these attribute literals will be possible to implement, will be possible to realize. Or in your hypothesis space, in that case we call it complete, because any target concept is included into that hypothesis space. So this is this form is we are allowing actually disjunctions of conjunctions of attribute literals. So when we have this kind of form, we know that this will have the power of expressing any Boolean expressions. So, for example, you consider these expressions in the same way we have represented here. So you see that it means that in either the sky would be sunny, or temperature is normal, or it could be temperature, it could be humidity, I'm not sure, but there is some attribute which is normal. Then again, either or sky is overcast, or there is a rain, or the weather is rainy, or the sky is rainy maybe, and say wind speed is weak. Or in all these cases, your output is true. So we can express the whole thing in this form by using the disjunction operations or operations. So naturally, this is a very powerful representation because it can express any concept, any Boolean expression in the form of that concept. And so hypothesis space is larger, and we call it also complete because when it represents all possible all forms of target functions in that with that representations. Now this can be represented as a tree. This this expression, instead of representing in this form, we can also represent in the form of a tree, and that tree we name it as decision tree. The advantage here is that it also tells you the process or the steps by which this expression would be computed. So it is the tree itself will tell you that no, in this way the computation should proceed. So it will specify that, because no, you have to start with the root node. So every node is in that tree is representing certain attribute, and every branch that will be a test conditional branch on which the attribute value will be true, then only that branch will be taken. So it will define a path of expression evaluation for every disjunction. There is every conjunctions in this disjunctive form, there is a path from root to leaf, and you are evaluating it. So let me explain with respect by giving an example. You consider this is a tree, and you can see that in the tree, the nodes are represented by those rectangular boxes. And then we have the edges, and each edge is labeled by a an attribute value. Okay, so your branching takes place if the value of the attribute is no, it is satisfied. Like outlook is the attribute. If its value is sunny, then it will take that path uh, for evaluation calculations. So, and finally, you will see also that there are leaf nodes which are marked here in red color, and there are two types of leaf nodes, no or yes. So those are the levels, or those are the outputs of the expressions. So every path will terminate at a leaf node, and that will give you the result of that expression. That expresses the result. So in this way, the expressions could be evaluated in this no, in this tree. So we are explicitly also providing you the conditions, no conditions also. We are explicitly providing these conditions. So I hope it is clear that how the expression would go, and you can see that how it is also equivalently expressed by this by the the expression given in that no disjunctions of conjunction form. That means if I consider, say, suppose this is the expression we are implementing here, you can see that this path corresponds to this part of the expression. Similarly, this one corresponds to this part of the expression, and no, this one corresponds to this part of the expression. So only in a Boolean expressions you are keeping only the true conditions, because if it is satisfied, then it is true. If it is not satisfied, then it is false. So it comes automatically. But in the decision tree, we are explicitly also computing the other conditions. Right. So it beats the other characteristic that we also take decisions in steps like this. So it's a kind of analogy with the way we also take decisions on certain matters. Another example of this kind of concept of decision tree. Uh, Say this example is say this problem is that, say, suppose I give you the labeled points, set of labeled points in a two-dimensional space, and the labels are shown here already. They are positive or negative. So it's a two-dimensional coordinate space. So is there any rectangle? I mean, you can consider a classifier in this way that you have to identify a rectangle. So any point within that rectangle will be positive, and the point outside will be negative. So these are the training examples, of course. So to make it consistent, you have to find whether there is any rectangle which is consistent with this kind of level. So this is the kind of learning. Please hold on. I have all to take. Okay, so let me continue. So I hope you have understood the rectangle learning problem. So we are learning a rectangle so that all the points within that rectangle would be level positive and outside would be level negative. So given the training examples, whether you can find a rectangle or not. So naturally, if you have a single rectangle, it's a single rectangle learning if you consider, and you have certain constraint. You cannot have all kinds of training examples. You cannot learn with a single rectangle, as you can understand. With that means which is consistent also. But if this is the form of hypothesis, then no, you are presenting your hypothesis only in the form of a single rectangle, and which we call as a conjunction, because what you are checking when you are checking the
The
of the rectangle. Yes, any question? So I think there is no question. But no, you consider a situation where you have you are allowed also to specify multiple rectangles in that set. So for a point which is included into any of this rectangle will be level positive. So that is the case of disjunctions of conjunctions or union of rectangles. So it's a kind of similarity. So this can be also implemented using a decision tree framework. So let us discuss with respect to these training examples, which are similar, bit similar with respect to the previous one. But as you can see here, we have certain records, certain observations, and each day record, 14 days records are here. But there are 4 attributes. Earlier, we have taken 6 attributes in our example. Here it is 4 attributes, and we also consider whether we should play tennis with that condition or not. So there are 2 conditions, either yes or no. And the example of decision tree is given with respect to this only. So there are 4 attributes. So here. So this is a decision tree with respect to that that we have already considered. And if I just to summarize what I said, that each internal node tests an attribute. That is the steps of computation of decision tree. Then each branch corresponds to attribute value, and each leaf node assigns a classification. And it can be represented by logical formulas we have already seen. But we can use it also in the form of your the concepts. That means that conjunctions form of concepts we can use. For example, in this case, this could be represented in this form also. Right? This is a concepts you have learned. So each conjunctions is a concept, and the disjunctions of these conjunctions are shown here. Hope it is clear to you. The other way of understanding decision tree is that actually each path of the decision tree gives you a rule. So you can consider that path for each path, and then that conjunctions can be expressed as a rule, and you can make a composite rule like this. So some of the scope of the decision tree, why you should apply when you are considering the decision tree. First thing, you should understand that decision tree has to be a finite tree in your computation. So the instances also, there should be finite branching options. So that's why these instances should have a fixed set of attributes and their values. That means they should be of discrete variables. If they are continuous variable, you have to again convert them into a certain form of discrete variable. So that is one kind of requirement. The other kind of requirement is that, see, you have only leaf nodes. So those are also discrete. So you should have your target function should be also of discrete value. Say it could be 2 valued or it could be n valued, but it should be discrete value. Again, no, discrete functions any continuous functions can be approximated by discrete functions with certain bounds of errors. So you can map your problem to a decision tree problem in this way with certain approximations. So it's a disjunctive hypothesis space. Also, it allows possible noisy training data, or possibly noisy training data. That is the considerations when we consider decision tree. Like when in concept learning, we have assumed that there is no error in the training data, and we are trying to find out only a consistent hypothesis. But now onwards, we will consider that your training data also contains may contain error, and in the perspective of decision tree and rest of our discussions with various other approaches, we'll consider there would be noise in our training data. There could be errors there could be missing values, some attributes, values may not be available, etc. So we'll see some certain situations also how to handle them. Some of the examples of where decision trees are very much used, like medical diagnosis, even equipment, fall detections in equipments, credit risk analysis, calendar scheduling preferences, etc. So just to give you an example, how a decision tree is formed. That means how do you decide about the node and the branching? Because that is the question. So when you form a decision tree, you have to think about that first. That you have to. It's a kind of top-down approach. So you have to start with the root node, and you have to decide that which attribute to be tested in that root node, and then after decision deciding that, then of course you can consider branching based on attribute values, and you can proceed to the next level. There also at every level of the path you have to select an attribute which is not yet seen in that path itself. So in that path, in that sequence, because you are checking the sequence of attributes, so at every level we'll be considering an attribute set. So in different paths, this order of attribute sequence checking may be different. But at every level, you should, in the path, there should not be any repetition. Over the path, there should not be any repetition of attribute checking. That is another kind of constraint while forming the decision tree. Here, with respect to this example, let me explain some of these issues regarding this. So once again, we consider this rectangle learning case, and that is multiple rectangle learning in a decision tree. So you have this attribute 1, which is, you can consider here x coordinate, and attribute 2, which is the y coordinate of a point. So your decision making process would be that you check with certain attribute 1. Okay, so I will tell you there are some issues. Yeah, so you check with certain attribute. You have to select one attribute and test the value. Since it's a continuous, it's a kind of continuous value, because x coordinate you can make it discrete values, but if you assume it's a continuous value, so in this case you have to discretize your options. So whether attribute value is greater than and less than. So these are the two operations you have to consider here. Either the value is, if it is greater than this, then it should go to the next level of your tree hierarchy, like next level of checking in one path, and if it is less, it will go to the another path. So in this case, so you have to draw axis parallel lines to separate the instances of each class. So you see that suppose I choose this particular particular axis parallel line, which means actually effectively what I mentioned, I have chosen a value of attribute 1 or x coordinate. So if the x coordinate is greater than that value, you are going to one side of the straight line, right? You are going to the region of testing points in one half of the this vertical line. These are all axis parallel lines. So either here I can say at the right side or left side, and when it's horizontal, I can say up or bottom. So at the right side, if it is greater than. If it is less than, we'll go to the, say, at the left side. Now, then again, suppose you went to the left side, and actually you found that in the right side every node is positive. So you can say that, okay, in that case we come to the end. and we can declare in your decision tree any point in the right side of the first axis parallel thing, like right side of this particular line is positive. So you come to a leaf node, so there is no need of explorations further. But the other branch, you know that in your as per your training examples, there are mixed levels. Points are there are two types of levels are still available. We call them as impure node. So this node is an impure node. So we are moving to an impure node. So you should again go on splitting into the regions. So let us once again you see that checking attribute. So my statement that in a sequence it is not repeated, it needs to be corrected. It can be repeated, but in some algorithm we enforce that property. It depends upon the domain of applications, right? So so you get another axis parallel line here, and now you see that here also you have this with respect to this line there is right side and left side, but your region also you should consider, because already when you are moving to this region, your region of the space is also partitioned. So you are only restricted with the region left side of the first axis parallel line which you have, or first vertical line which you have considered. So now with respect to that, left side of your second vertical line in this node, that is also pure. But in the right side, you will find, sorry, right side is pure, but the left side you will find it is impure. I mean, just to make it clear. So this is the right side, right region with respect to this vertical line. So it is pure because all are negative, negatively leveled. And this is the left region of this vertical line. So it is impure. So we are going to split this region once again. Now here, you have the options of both attributes, and you will find that the appropriate line that you should choose for the attribute with respect to attribute 2. And you can choose a line such that now you get both left and right regions are pure nodes, which means that now you have come to the end. There is no impure node to be expanded. So in this way, actually, the decision trees are formed. So you have been given the labeled training examples. You are partitioning these training examples based on certain attribute value, so that you try to get as close as possible to pure nodes. Because if you get a pure node, then you are not going to expand. So your tree remains small, tree depth remains small. Now that is one kind of heuristics, one kind of desirable property, I should say. There could be many other solutions. It is not unique, as you understand. It is not a unique solution. There could be many other solutions which will be still consistent. Like I could have split even the pure nodes, and I could have said that this is positive, etc. Or any other way that impure nodes you can get. If I simply consider in the first splitting itself, say instead of this line, if I consider this line, so naturally you see that you have to split both this side and this side, and your tree will be different. But anyway, that tree will be still consistent with respect to these levels. But your algorithm should be such that your tree depth is also kept small. Now, it is optimally, I should say, as an optimization problem, I would like to derive a smallest depth decision tree. But that's an NP-hard problem. Combinatorial, that's an NP-hard problem. But by applying heuristics or by applying greedy method, we can design an algorithm which will satisfy, which will have a good property of, which will have low depth of tree or small, which can keep the depth small. So we would be discussing those approaches in subsequent lectures. So I just mentioned this thing, so let me not repeat further, but I hope this is understood with respect to these examples, right? So you see that I mentioned that alternate splits are possible. Then decision nodes, there will be a condition. Then you go to a particular box, particular region, and you check the samples in that box whether it is pure or impure. So every branching will give you take you to a partition of that space, a partition of the space in this particular problem. And in that space, whatever training examples are there, you are looking at those training examples which are whether they are all leveled, whether they are leveled by a single uniformly or whether they are differential levels. So if I put it in the algorithmic structure, as you see, it's a top-down construction. So start with an empty tree. Then in the loop, you are splitting the best decision attribute for next node. So attribute selection is a task that you need to do at every node, that which attribute should be selected, whether attribute 1 or attribute 2, which means whether the x coordinate or y coordinate in the previous problem, right? After that, of course, again, you have to consider, because if it is discrete value, your job is simpler, because for every discrete value, you'll have a branch. But if it is a continuous variable, then you need to discretize. So what kind of discretization would be efficient, would give you the desirable result? That is an issue. But let us consider you have a discrete valued variable for the time set in this case. So after getting the attribute, then with respect to each value of a, as I told, that is already given to you, that these are the possible values on which the branching would take place. So you create new descendant node, a descendant of that node, and or you can say a new child node, and you sort training examples. Sort means you consider those training examples which should be associated with that node. That means with respect to this branch, which are satisfying the branching condition. That means whose attribute A, value of A, is the same that of the value used for branching. Then only those examples come under this scope, and then you check its levels. If its levels are uniform, all are same, then it's a pure node and it becomes a leaf node. If it is not, then again you go on selecting another attribute, appropriate attribute, and go on doing these things. So this is what you do. If training example is perfectly classified, then you stop. Otherwise, iterate over new leaf nodes. Now, since you are for the discrete case, as you see that the property I told, that in a path from root to leaf node, an attribute is not checked multiple times because of this only. Because already you have ensured in one of these nodes that all attribute values are same. That is the sorting part. So there is no need of checking the attribute value further. But the example what I have given, unfortunately, it is not that case. No? There is graded values of that attribute. It is not that every value of the attribute is same. So that's why in those situations, you have to select, you have to consider again repetition, again whether those attribute values are going to be checked or not. I hope now it should be clear. And with respect to examples, we can again further elaborate. So grow tree just deep enough for perfect classification. So if possible, you can approximate at chosen depth, which means that it is possible that you can satisfy all training examples using a decision tree. You can go on branching at every point, as you see that finally you get at least one example with that level, and that is the uniform level, and you come to that leaf node. So theoretically, you can get a decision tree which will be consistent with respect to training examples. But the problem of overfitting may come because, as I mentioned, that your training example may be noisy. And not only that, there could be various other, so it is data dependent now. It has become data dependent. If you, from the population, if you randomly sample other set of training examples, you may come up with another decision tree. So which is quite different because so there could be various consistent hypotheses with respect to data dependent consistent hypothesis you are getting. So that's the case of overfitting. So you'll get an overfitting because the generalization power would be poor. So that's why what we do instead of going into that deep for a decision tree and satisfying every training examples, what we try to see that largely the tree nodes should have at least certain number of examples. Every node should contain certain number of examples at the end. That pure nodes should be of sufficient strength. Now, if you can ensure that, it may be, sometimes you have to also allow certain impure nodes because of that property that largely nodes are uniform. There may be a few exceptional cases, but we can consider they are the noise. So in this way, the noise is handled in decision tree. There are various mechanisms for that. I'm just told you in a naive manner how we understand that a decision tree, the depth of the decision tree, choosing appropriate depth of decision tree is also a kind of a major issue, and it is not desirable that you grow decision tree to its fullest extent, satisfying all training examples. So the question here is that which attribute is best, how deep you should grow the tree. Those are the questions. So again, we come to the same examples. These examples with respect to these two attributes, as I say, these are continuous value attributes. So attribute 1, and I think this is repeating what I have mentioned, right? So this should be also a bit repetition of my explanations. So you can form a tree with pure labels, and so you are trying to do correct classifications for the training examples, but I told you the issue is there. So a greedy approach that I was mentioning could be like this, that initially you treat the entire data set as a single box here with respect to the two-dimensional example, two-dimensional the classification examples with respect to coordinates. So we can consider the entire data set as a single box. And then for each box, choose a split with an attribute that reduces its impurity. So that attribute should be chosen, which will reduce the impurity, because your box is impure because you have all sorts of training examples, all kinds of leveling of training examples initially. But if you choose and if you can ensure that your partitions have some uniformity, that means in one partition you get more or less, or in both the partitions, this impurity can be less. So one measure is entropy measure, as you understand that entropy is a good measure. You try to make entropy low because you want one of the levels to occur with a higher probability, right, in every partitions. So in every partitions, you try to see that one of the levels should occur with a higher probability, which means entropy of that partition would be low. So there are many other interpretations, but entropy-based interpretation is easier to understand. That's why I mentioned it. So, if I consider the whole region, entropy of the whole, the first box itself, as it is mentioned. So you can compute entropy because you know the distribution with respect to training examples. You know the distributions of levels with what probability a level occurs. So you can compute its entropy. And if I consider a particular split, suppose you have identified an attribute value. Given an attribute, given a value, you can always sort training examples into two partitions. That means in one partition, which will have that attribute value, in other partition, which will not have that attribute value. Even you may consider all possible attribute values because it is discrete. If there are n attribute values, there will be n partitions with respect to that. For each attribute value, there will be one partition. So there will be n partitions. And for each partition, after sorting them, you look at the distribution of the class distribution, level distribution of the levels of classes. Again, you compute the fractions of levels in each partition. You compute entropy in each partition. So the aggregation of this entropy, aggregation of this entropy, or average entropy, if I say, this average entropy, it could be weighted average also, because some partitions will be will have more elements, some partitions will have less elements. It could be weighted average with respect to their proportional number of elements. So anyway, so this weighted average of entropy should be less than the entropy of the parent node, right? Entropy of the parent node. I mean, you expect it should be less because of the sorting. Now, which attribute will reduce it the most? That is the question. So given an attribute, if you really go on this partitioning with respect to this, you will have entropy, weighted average of entropy will come down, right? But the question is that which attribute is less? So this is the way you can choose an attribute, right? So that's what you split the box having highest reduction in impurity. That is the highest reduction. So there will be a reduction if you sort this, but which attribute gives you the highest reduction? So you should continue till you get your nodes, all nodes pure, or to a great extent they are pure, right? So this is what. Then you stop when all boxes are pure. So any question? So let me give this example and then I can take your question. See, you consider this example that this attribute I'm representing two attributes, A1 and A2. Suppose with respect to a, so suppose originally in your, when you have started, or in the domain, in that parent node where all the training examples are considered, the node there are 29 positively labeled samples and 35 negatively labeled samples. And based on attribute A1, if you sort, so attribute A1 has these two values, either A1 would be true or false. These are binary attributed values. So if A1 is true, then you will find that out of this, whose value of A1 is true, in that distribution, 25 are positive and 5 are negative. And where A1 is false, in that distribution, 4 are positive and 30 are negative. And so similarly, you have also the conditions of A2. Now, this is a different example. So don't look at it. Right now, don't look at it. Okay? You just consider these two situations. So at this point, with respect to A1, you have this distribution, and with respect to A2, you have this distribution. Now you can compute the entropy. So what happens? Oh, this computation is shown later on. I think let me go to the computation, because entropy should be, I will come back to this. So this is what I was showing you. As I mentioned, that don't look at this. Just look at this example. So the entropy of this one is 0.993. Can anyone tell that how this computation is done? I have not shown you those slides. I can go back and I will show you. But I would like to know whether you know that how this computation could be done.
Sir,
how do you get this entropy of that? Yeah.
Sir, the weighted mean of those terminals nodes entropy, like
no.
Means
My question is that how this entropy becomes 0.993 for this distribution. See, we are considering entropy with respect to this distribution.
Sir, at first we have computed the entropy for these two terminal nodes. One is 0.650 and another is 0.522. And then it will be 30 by 64 into 0.650 plus 34 by 64 into 0.522.
And that would come as 0.993.
Yes, sir.
How do you say? Because it has to be less than, it has to be between 0.650 and 0.522. How it becomes average of 0.650 and 0.522, how it could be 0.993? So it is not true. You have not understood this concept. Anyone? Anyone else? There is no answer?
Sir, maybe 29 into log of 29 by 64 plus 35 into log of 35 by 64.
Sir, it will be a minus of a positive value. The positive value is given over 29. So minus 29 by 64 log of 29 by 64, and then minus of negative value. The value is 35. So 35 by 64, then log base 2 of 35 by 64.
Good, good, very good. Actually, yeah, you know what is meant by entropy. You understand? Just let me. Yeah, so let me use this pen itself. See, I will come to this slide later on. I mean, see how entropy is defined. I mean, the thing what you define, what's your name? Because I cannot see or check your name. Who has answers?
Sir, Shoham Banerjee.
Shoham, okay. See, the thing is that when you consider entropy of a distribution, distribution means what? Probability distribution. So you find out what is the probability distribution of these levels. That is what is we are looking at when we are trying to check whether the levels, whether a node is pure or impure. Pure with respect to what? Pure with respect to uniform levels. Whether all the levels are uniform, which means probability of a level is 1. Of any level is 1. Other will be 0 naturally, if there are 2 levels. If there are multiple levels, then one of them level would be 1 and all other would be 0. Right? So if you consider the probability of level, positive level is say P positive, that you can compute what you have said, what Shoham said, that is 29 by 64, isn't it? There are 64 samples. At this point, you are checking 64 samples. At this node, when you are testing, this node is associated with 64 samples. Suppose this is parent node, which means all the training examples. Suppose there are only 64 examples, which we have already mentioned here also. Right? So, with respect to that, what is the probability of positive samples? It is 29 by 64. Is it clear? Then what is the probability of negative sample levels? That would be 35 by 64. So how do you define an entropy? If you remember, the entropy actually, it is basically weighted average of log 2. See, this is the definition of a particular observation. That is the entropy, measure of entropy. But you have to consider the weighted average. That means the probability of all this. So that is the definition of entropy itself is like that. Of course, you have to take minus. Minus of log 2. Log 2 of 1 by p. It is not log 2p. It is log 2 of 1 by p, which means minus of log 2p. That is the measure of entropy. So this is what is your entropy. If I write E, your entropy is this. And why I have written S? Because this sample S consists of this. S is the whole set of your training examples. So that's why you see that you are computing 0.993 by doing these things. You are basically computing for the positive level. You compute this, then you compute for the negative level, right? It's the same item, and then you basically add them. Of course, this minus sign has to be considered after that. I mean, this is the definition. You just compute it, then you will get this 0.9. It is not the weighted average of this two. Similarly, how do you compute this? Because once you have sorted these training examples, out of this, you find out that value of attribute of A1 equal to T, true. For that, 25 of these 29 positive examples will be having the value of attribute A1 true, and 5 of the 35 negative examples will have the value of A1 as true. Is it clear? So now this is your distribution with respect to when the value of A1 is true. When you consider a branching with respect to this, then you are getting this kind of training example. This is a region this is a set that is associated with this node. Now, what is the entropy of this node? That is the question. What is the entropy of that node? Anyone? How do you compute this entropy of this node? So
we can similarly do like 24 positive, 25 positive, and we have total 30. So we calculate positive probability.
So in the same way you can compute. Yes, you have to answer me, otherwise my speed will be slow. And somebody complained in the previous class, but no, you have to respond. Because it is difficult for me from here to know that you are understanding the thing. I cannot see you. So unless you respond, it is very difficult. At least one of you should answer. So yes, how trivial it may be. It may look very trivial, but please answer. So that is the thing. You are using the same method of computing entropy for this distribution, and you get 0.650. And that is also true for this one also. For the same method, you get 0.52. Now what you do with respect to this attribute, these are the two partitions. You have computed entropy of this partition. You have computed entropy of these partitions. Now you take the weighted average of these two entropies. That is the weighted average. So someone is telling this weighted average thing. I mean, probably you have gone through some of this text, but you need to understand what is meant by this. So why are you checking? Because you would like to see whether your entropy level, how much it is reducing. So that is your entropy level with respect to this partition. Yes, the question is there. Any question?
Sir.
Yeah.
Sir, why is the entropy is the best measure? Why not weighted average? Like in these 4 examples, we can easily say that the first one is the best tree.
How? Easily means by visually looking?
Yes, sir. Because the distribution is like
in a computer. So that is what we are trying to model. That is what we have to compute. No? Visually, by looking at it, sometimes that would be also difficult. It may look very obvious in this example. But this is, I told you, this is one measure. There are other measures that I will discuss. Because if you have an idea what is entropy is representing, if you have realized that, then you readily, intuitively, you can understand why entropy could be used as a measure here. So there lies that intuition. You need to understand what is meant by entropy. That is the basic thing. So since this question has come up to you, so please go through the text of probability theory, of the information theory. Then you will understand the definition of entropy. So entropy low means there is a order in your randomness is less. That means you will get more levels, uniform levels in this case for the training example. So it is easier to predict. If entropy is zero, entropy is zero, which means that I can, given any training example, I can immediately say, because all are positive, I know this, all are positive. This information is sufficient, all are positive. Only that information you need to know.
Yeah, yes, sir, but
so
by considering
example,
here we are taking A1 attribute, right? And we are even calculating the probability of positive output.
Positive output?
P plus.
You have to take a decision whether this is positive or negative. Both the decisions are important.
Yes, sir, but why can't we stop there, right? Stop there, and if P plus is higher, and why can't we make sure that is the perfect tree like that? Even in this entropy also, if P plus or P negative is higher, then entropy. So why can't we stop there? Like if P plus is higher, then that is the best tree.
See, how do you say P plus is higher? And you just try to, yes, you please do it, because this question has come. You have to think it deeply, right? So you try to computationally identify that. You can consider all different kinds of sorting. Suppose the P minus could be also higher. As you are saying, you are trying to intuitively say that P plus is higher, so I should stop here. this slip node should not be.
Yes.
This is a pure node. That's what you are saying.
I am saying if P plus is higher, the entropy will be obviously lesser. So why can't we take P plus
But at
is,
the other end, suppose at this end, if you have both are similar. At this end, suppose this is 4 plus and 4 minus. Suppose both are similar, then the entropy of this node
okay,
is quite,
sir.
right. So in this partition, so with respect to the whole
Then
partition,
entropy will be higher. Then entropy will be higher compared.
Entropy would be higher. Yes, entropy of this node would be higher compared even to that also can. But if you take the weighted average, there will be reduction of entropy. So our question is that suppose with respect to A1 you get a reduction, with respect to A2 you get a reduction, then which one is the highest reduction? Okay, so let me proceed, and you can understand better if I proceed it. So let me go to this. Now you can see the bottom example also. So the top one seems to be very obvious. I told you that this is a different situation. So you have now you consider this example, the bottom example. There you can see, as you are asking that question, that here this is the entropy 0.708 and 0.742 and 0.937 and 0.619. Right? Because of this, you understand that.
Yes, sir.
Now, if you take the weighted average, which one would be lower? Which one would be lower with respect to the reduction would be lower? Actually, in this case, since you are just which one would be lower, that would be fine.
Yes, sir.
So there you have to take weighted average. So let me go through. Yeah. So with respect to this example, let us see. So this is the gain 0.395, the first case, right? The first case of distributions, this is a 0.395 and this is 0, no gain. So we have defined a gain. Gain is the difference between weighted average of the entropy of the partitions and the original entropy of the original set. That means non-partition set, the whole set. So here, should see the entropy of the whole set is 0.993 and weighted average of these two would be in between these two. Like the weights would be 25 by, this is 30. There are 30 samples, so weight should be 30 by 64 and this weight should be 34 by 64. Right? 30 by 64 into this, 34 by 64 into this, plus then you will get whatever value you get. That value, if you is less than by 0.395 from this value. So that is the gain. But if you take the weighted average of these two, you can see here also this entropy, in fact, it becomes higher than the parent term. But if you take the weighted average, incidentally, they remain same. So the gain is 0, right? Consider the bottom one. Here you can see in the case this is gain is 0.265, the other gain is 0.121. It was not very obvious, but just by looking at with this option, you should select attribute A1 in the second case also. Now it depends upon that how what is your training examples, what is the kind of distributions, but this is the mechanism by which you can choose your attribute set. So I am almost at the end of my talk. So I think let me stop here. I have already defined this entropy. So please read the information theory and also the definition of entropy, the implications of entropy, that is what. And then you see that this is the method and this is the definition of information gain, where it is the difference of entropy of the original set minus the weighted average of the entropy of the partitions. So that is what is entropy gain. And from there, you select that attribute which has the highest information gain. That is the attribute selection process. So you should consider all possible attributes And with respect to that attributes, you should consider the sorted training examples into different partitions and compute this information again. And then you select the attribute at that node. And in this way, recursively, you can proceed. Because once you have selected, then you got all these partitions. Their nodes are defined. In the next level, once again, with respect to those training examples which are associated with that node, satisfying that branching condition, again you iteratively apply this method. But I mentioned that if the attribute values are discrete, so there is no there is no chance that the attribute values will be different in subsequent nodes of that path. So you don't require to revisit this attribute, which means if there are n attributes for discrete values, with n such at every path there would be at most n such checks to come to a particular conclusion. So with this, let me stop here. Just to announce a few things. First thing is that in the previous class, that I had a confusion that while discussing about the probability of whether your hypothesis space consistent version space is epsilon exhausted or not, that I considered, in that case, I said probability, that is the probability whether it is exhausted. Actually, it is the negated one. So the expression is for probability that version space is not epsilon exhausted. I mentioned that during my lecture. So you need to note that correction. If you read the book, you will find, in fact, that is the case. The proof was basically which is computing the probability whether the version space is not epsilon exhausted, and then that expression that it should be bounded by that size of the hypothesis space and that exponential term e to the power minus of training example and d epsilon. This is one thing I would like to mention. The other thing is that your first quiz tentatively it will be held on 9th September. That is on a Thursday. In the same time, the topics would be this concept learning and also decision tree. So I will also further give you the details, but just to let you know at this point. Okay, so thank you very much. Okay.